So remember before that we talked about the projection onto a subspace. And let's just go ahead and visualize again what that might look like in 3 dimensions. So let's say that we have some subspace in 3 dimensions, and maybe the subspace is a plane. So that plane might look like this. We have a plane like this, and then like this. And so just this generic plane. And we said that if we wanted to project onto that plane some vector, so let's say the vector looks like this, and then the projection of this vector into the plane might look something like this. So let's just say that's the shadow of the vector. We'll call this vector the vector x, and then we know that the projection vector is the projection of the vector x, we'll say onto the plane P, if we call this the plane P. What we said is that this projection vector, the vector in the plane, this is the closest vector that's in the plane to the vector x. So if the vector x is not itself in the plane, it sticks up above the plane or below the plane, so it is outside of the plane, then its specific projection vector, the projection of x onto P, that is the vector that does exist in the plane, which is the closest possible vector in the plane to the vector x. We want to keep this idea in mind as we start talking about the least square solution, because the least square solution is a solution that we find to the equation ax equals b when there is actually no real solution for the vector x. So normally, let's give an example that does actually have a solution for ax equals b. Let's say that we have some matrix, we'll call it 2, 1, and then 1, 0. And then we have the vector x, and then we have some solution vector b. Let's say that the vector b that we choose is 5, 2. And then let's say that we also rewrite this vector x. We'll rewrite it in matrix form, so we'll call it here by its components, x1 and x2. What this equation is really telling us is that we have a system where we take the first column vector, 2, 1, and we multiply that by x1, and then we add to that x2 multiplied by the second column vector, 1, 0. So 1, 0, and that's equal to 5, 2. And we're looking for the values of x1 and x2 that make this equation true. In other words, how many of the column vector 2, 1 should I combine with how many of the column vector 1, 0 in order to get the column vector 5, 2. And what we can see is, I picked this vector specifically, this 5, 2 vector specifically, is that if I use 2 of this first column vector, so if x1 is 2, and I use 1 of the second column vector such that x2 is 1, then I can see here that I'm going to get 2 times 2 is 4 here, plus 1 times 1 is 1. I'll get 4 plus 1 is 5. That gives me my solution here. Then if I get 2 times 1 is 2, plus 1 times 0 is 0, 2 plus 0 is 2, and I have my solution. So what we're saying is that the solution x here, the vector x, tells us how many of each of A's columns we should use, we should combine together in order to get the vector b. In this case, in order to get the vector b 5, 2, we should use 2 of the first column of A and 1 of the second column of A. If we combine those together, we'll get the vector b. So the solution then is x1, x2 is equal to 2, 1. That's the combination we should use in order to get the result 5, 2. The fact that we were able to get this solution tells us that the vector 5, 2 is in the column space of A. Because remember that the column space of A is the span of A's column vectors. So we'll say the span of 2, 1 and 1, 0, the span of these two vectors. And remember that the span is all the possible linear combinations of these vectors. So what we're saying is that, for example, the column space of A would include the linear combination where we take 2 of the first column vector and 1 of the second column vector and combine them together. That's going to give us the vector 5, 2. So 5, 2 is in the column space of A because 5, 2 is a linear combination of these columns. It's the specific combination 2 of the first column and 1 of the second column. In other words, when we have this generic equation, ax equals b, what we're saying is that there is a solution to this equation. There's a possible x, there's a solution to the equation when b is in the column space of A. But sometimes you're going to have the case where B is not in the column space of A, which means that there's no combination of A's columns that we can put together in order to get B. When that's the case, when B is not in the column space of A, such that we can't find a solution, X, that's when we want to go to our fallback solution, which is this least square solution. And the least square solution is actually going to be the projection of this solution vector X onto the column space of A. So if we again go back to this visualization, instead of saying that this is just the plane P, let's call this plane the column space of A. Remember, the column space is a subspace, so let's pretend for a second that it's a plane. And so this plane represents the column space of A as a subspace. We already said that this projection vector, when we have some vector x that's outside of the subspace, the closest possible vector that's actually in the subspace, the vector that's actually in the subspace and as close as possible to the vector x is this projection vector. So what we're saying here is that when B is not a member of the column space of A, then we'll settle for the least squares solution, which is going to be the projection of B onto the column space of A. So we could think about this, instead of the projection of x onto P, we're going to think about the projection of the vector B onto the column space of A, where this is the vector B. So B is not in the column space of A, it's outside of it, which means that there's no real solution for the vector x here. So we'll take the next best thing, which is going to be the projection vector. That vector is actually going to be in the column space of A, so that vector will actually satisfy ax equals b, and it's going to be as close as possible to what would be a solution if there was one. And we actually call this projection vector, we call it x star instead of x, and this x star is the least squares solution. So that's the vector that we want to be able to find. Now to find that vector, that x star vector, the least square solution, we're going to use this formula, A transpose A times the least square solution is equal to A transpose times the vector B. So to actually show you how we use this formula to solve for the least square solution, x star, let's say we've been given some system of equations and maybe it looks like negative 2x plus y equals 1, and then negative x plus y equals 0, and then x plus 2y is equal to 3. Now, if we were to graph these three equations, let's go ahead and get rid of this. If we were to graph these three lines, let's go ahead and set up a quick set of coordinate axes like this. So we have this system, and let's call this 1, 2, 3, 1, 2, 3, 1, 2, 3, and 1, 2, 3. So that should be good. This first one here we could rewrite as y equals 2x plus 1. That means we're going to have a y-intercept of positive 1 and then a slope of 2. So we're going to go up 2 and over 1, and then here down 2 and over 1. And so our line there might look something like this, let's say roughly. So that's our first one. The second equation here, we have negative x plus y. Let's turn that into y equals x plus 0, or just y equals x. So that equation we know goes through the origin here and then has a slope of 1. So we can go ahead and connect these points, and that line might look something like this. And then the third one we'll call 2y equals negative x plus 3. And if we divide both sides by 2, we'll get y equals negative 1/2 x plus 3/2. So that has a y-intercept of 3/2 or 1.5. So that goes right there. And then its slope is negative 1/2. So we go down 1 and then over 2, something like that. So if we sketch that in, it might look like, let's say, here. So now we've got a rough picture of what these lines look like, and you can see that they don't all intersect each other at one single point. We have an intersection point down here, we have an intersection point here, and an intersection point here, but there's not one single solution. If there was a solution to this system, then all three of these lines would intersect each other at one point. But because they don't intersect at one point, that means that there's not a solution. B is not in the column space of A. So what we have to do instead is find the least square solution. So we want to start by putting this system into a matrix. So if we take the coefficients on x, we have -2, -1, and 1. And then the coefficients on y are 1, 1, and 2. And then we could say that this matrix multiplied by some x, y, which are the unknowns in our system, if we were setting up our ax equals b, it would look like this. We would take the answer column matrix 1, 0, 3. So 1, 0, 3. And what we're saying here is that this is A, this is X, and this is B. And we're saying that the vector B is not in the column space of A, meaning that I cannot take any combination of A and B. I can't take 2 of the first column and 3 of the second column, or -4 of the first column and 1 of the second column. There's no linear combination of the columns of A that I can put together that are going to get me to this vector B, 1, 0, 3. And so because of that, because B is not in the column space of A, there's no linear combination of the columns of A that I can use to get to B. That means there's no solution X that I can find. I have to use the least square solution instead. So to use the least square solution, you can see that the first thing we need to do is find A transpose. We already have A right here, so we know that. A transpose is going to be equal to -2, 1, -1, 1, and then 1, 2. And then for our left-hand side over here, we need to find A transpose A. So we'll say A transpose A is going to be equal to, we'll take -2, -1, 1, 1, 1, 2, and multiply that by A. So -2, 1, -1, 1, 1, 2. So we're going to take this dot product here, and when we do, we'll get a 2 by 2 matrix here. So we'll say -2 times -2 is a +4, -1 and -1 is a +1, 1 and 1 is a +1, and then the first row by the second column, so -2 minus 1 plus 2. The second row by the first column is going to be -2 minus 1 plus 2, and the second row by the second column gives us 1, 1, and 4. So the result there then is 6, -2 minus 1 is a -3, -3 plus 2 is a -1, -2 minus 1 is a -3, -3 plus 2 is a -1, and then 1, 1, 4 is 6. So this is A transpose A, and then we also need, for the right-hand side here, A transpose B. So A transpose B is going to be equal to, we'll take A transpose -2, -1, 1, 1, 1, 2, and multiply it by our B, 1, 0, 3. So 1, 0, 3. The result there is going to be a 2 by 1 matrix. So we'll say the first row times the column is going to be -2 plus 0 plus 3. And the second row times the column will be 1 plus 0 plus 6. And so that's equal to -2 and 3 is a +1, and then 1 and 6 is 7. So that is A transpose B. So now if we set up our matrix equation, or our least squares equation, we'll have to keep this A transpose A. So we'll get rid of this. We know that this is A transpose A. So plugging everything into our formula here, we have A transpose A on the left side. So we have 6, -1, -1, and 6. And then we have our least square solution, so X star. And then that's going to be equal to A transpose B, which we already found is 1, 7. Now notice that basically what we've done here is take the original matrix equation up here, A times the vector X equals the vector B, and we've changed it into this new equation. So we have this matrix multiplied by this vector x is equal to this new solution. So this is going to give us the best approximation of the solution if there was actually a solution. And so to find x star, all we do is augment this matrix with the 1, 7 matrix. So we say here 6, -1, -1, 6. We augment that with 1, 7. And then we put this into reduced row echelon form. So let's go ahead and switch the first and second rows. So we'll get here -1, 6, and then 7, and then we'll get 6, -1, and 1. Then we'll go ahead and multiply through the first row by a -1. That's just going to get rid of the negative sign here, and we'll get a -6 and a -7. Then we'll take 6 of the first row away from the second row. So the first row will stay 1, -6, and then -7. And the second row will say 6 minus 6 times 1 is 0. -1 minus 6 times a -6 is -1 minus a -36, or -1 plus 36, which is going to give us 35. And then we'll say 1 minus 6 times a -7 is 1 minus a -42, or 1 plus 42, that's a 43. Then we'll multiply through the second row by 1 over 35 to get a 1 in that pivot position. So 1, -6, and then -7. And here we'll get 0, 1, and then 43 over 35. And then we'll add 6 of the second row to the first row. So our second row will stay the same, 0, 1, and then 43 over 35. And our first row will say 1 plus 6 times 0 is 1. -6 plus 6 times 1 is 0. And then here for this spot, we'll have -7 plus 6 times 43 over 35. 6 times a 43 is a 258, so we'll get 258 over 35. And then 7 times a 35 is a 245, so we'll get -245 over 35 plus 258 over 35, and that'll give us a 13 over 35. So the result here is 13 over 35. Now this 13 over 35, this is approximately equal to 0.37, and this 43 over 35 is about 1.23. So if we were to plot this point, remember what we're saying here is that this is x star, this is the least square solution, is equal to 13 over 35 and 43 over 35. And if we were to plot that point, we would see here we get about 0.37, maybe that's right about there, and then 1.23, maybe that's like right about here. So that's our least square solution. What this is showing you geometrically is that this is minimizing the sum of the squared distances from this least square solution to each of these other points. In other words, it's trying to represent the best approximation of what the solution would have been if this system had had a solution. So again, there isn't a solution to this system, but if there was one, this spot, this least square solution, is the closest that we could get to it.